Okay, so like I was trying to explain here, I was saying what you're going to have is a situation where molecules are going to be repelling each other. So I'm trying to explain this energy you are seeing here, which is the static strain, because of the repulsion of electrons in the bonds. And then you have torsional strain, which is due to repulsion between pairs of, okay, so torsion is the one that is repulsion due to pairs of bonds caused by electrostatic repulsion of electrons in the bonds. So this is torsional strain. Then static strain is the repulsion between the electron clouds of atoms or groups. So say you have two groups that have unpaired electrons. So those electrons are going to cause these repulsions in these particular groups. And then there's angle strain, which is the destabilizing due to distortion of the angle from the optimum. Now, if I take you back, there was a point where we had, let me just take you to the first structure that we had so that you see what we're trying to talk about here. Okay, we have this here. We have these angles, 109 degrees, this angle here. So what is actually going to start happening is that when the molecule is rotating, these angles are going to start changing. So when these angles start changing, they will bring about what is known as angle strain. That angle strain actually destabilizes the molecule we are actually looking at. So those three are going to be of a concern when it comes to calculating. Though don't worry, you're not going to start saying, is this having torsional strain, or is this having angle strain? What is causing this? We will make an addition of these energies, and what you're going to be measuring or what you're going to be calculating is just a sum of all the energies that are present in a particular conformation. So we will give a table, or a table will always be given of energies. So for instance, if this is the energy if this is a molecule that you have, the hydrogens are eclipsing here. So this kind of eclipsing, hydrogen to hydrogen eclipsing, has a certain amount of energy. So that amount of energy will involve, if you check here, there is static strain that is coming because of the hydrogen atoms being close. Then there is torsional strain that is resulting because of these two bonds being close to each other. And then there's angle strain that also results because of the repulsions that are going to be there. So here, mostly angle strain is very negligible. So we don't concern. So the only two major energy here, destabilizing energies, are torsional strain and static strain, not angle strain. The angle strain, we will look at that one more when we start looking at cyclic molecules, because they are the ones whose angles tend to change mostly. So here, this is what you concern yourself with, and the angles that arise. So this is what you're going to have. So you have this particular molecule in the staggered position, and then what is going to happen here is that it rotates. You have this. So this is what is actually being explained here. You have 4 kilojoules HH interactions. You have HH interactions. You have HH interactions. So each HH eclipsed interaction is 4 kilojoules per mole. Each HH interaction is 4 kilojoules per mole. So if you check how many HH interactions does this particular molecule have, so this energy you are seeing is a sum of static strain and torsion strain. Okay, static strain and torsional strain, when you add them together, they'll give you that particular energy. So you don't need to worry about that. You just need to know that that is That is what this energy is. When it comes to you answering in a test or anywhere else, they will provide these particular energies. They'll just give you that. HH eclipsing is 4.0 kilojoules per mole. So when you're doing your calculation, that is a value you just get and then add how many of those are resulting on a given conformer that you have. All right. So this is what we mean by steric strain. So there is electron repulsion between these two hydrogen atoms. So as a result of that, there's steric strain within the molecule. Then angle strain will result as these angles have gotten, not angle strain. This is where you will not see the angle strain because these molecules are already oriented at 109 degrees in space. So because of that, angle strain is not going to be found in these ones. They're just, what is rotating is this bond here, and it is not changing the angle, it's just rotating. But when it comes to cyclic molecules, which you will see later, probably tomorrow, what you're going to observe is that when it rotates, the angle changes. And as a result, it brings in angle strain. So for acyclic molecules, steric strain and torsional strain are the two forms of energies that you're going to concern yourself most with. So here is how you do your calculations. You have HH eclipsed, which is resulting from torsional strain, 4 kilojoules per mole or kilocalories per mole. So you're going to be doing this. Find how many of these are in your molecule. The number you find is the number you multiply. And then you put these energies and then you multiply them by that number. And then when it comes to this particular diagram that you have here, this diagram, you're seeing the energy, the potential diagram. It can be drawn in two different ways. Okay, though this and the other one there are one and the same. So if you check here, ethene is going to come out like that. Okay, the molecule will just be changing in between eclipsed gauge, eclipsed gauge, eclipsed gauge, eclipsed gauge, and the energy difference is going to be the same. Okay, now when a molecule is a bit different, this is what I meant. You're going to have that structure at 180 degrees. Now, here you have energy in the y-axis, and you have dihedral angle in the x-axis. We can change this x-axis. Instead of saying dihedral angle, you say rotation angle or angle of rotation. Dihedral angle restricts you. You have to show the exact structure, okay? Meaning the first moment you're going to observe your molecule, what you're going to draw, you have to find out, is it at gauge or is it at eclipsed? Is it at anti-eclipsed, I mean. So you have to establish this. Now, this is going to be time consuming on your end, and it might make your drawing of the energy diagram a bit tricky. So what you should do is, instead of using dihedral angle, use rotation, meaning the first structure you draw when you start drawing your structure is going to be at 0, and your graph is not going to start like the way this is starting at 180, because that's the structure that was drawn first. It's going to start, it's going to start like this: 0, 60, 160, 120, 180, 240, 300, 360. So it's going to go like this. It's not going to start. So 0, you're not going to put a total eclipse structure at 0. No, you only put a total eclipse structure at 0 if you are using dihedral angle in the x-axis. If you change in the x-axis and you write rotation, you put the first structure you draw as the first structure that comes out there. This method is quick, safe, and it doesn't accord you to write mistakes if at all the energy diagram is asked of you to draw. Okay. The other one, this one here is a bit tricky. Once you make a mistake on which structure you begin with, the whole energy diagram is wrong. Only a cancellation is going to be given in that particular regard. All right. So here is now an example. You have 1-chloropropane. When you draw the two structures, you have this structure at 180, which is staggered, which is anti, this one is anti here, okay? So this is the anti structure. This is the eclipsed, which is total eclipsed. The two bulky groups, if you check, these are small groups. So these are the two bulky groups that you have, and they've totally eclipsed. So this is the eclipsed conformation. Now, like I said, when you do the calculation, every time you will find that the conformer, which has total eclipsing of the the large groups that you have, is the highest in energy. The structure which gives them 100% separation is the least in energy. So the one that is the least in energy is the most stable, and the one in high energy is the least stable, meaning your molecule will spend more time in this conformation than it will in that conformation. That's what that means. Your molecule will spend more time in this conformation than it will in that in this conformation. Now, you should know this just by looking, because it's not every time that probably they'll ask you to, and at this particular stage, I don't know how far you've gone in your chemistry, but I don't think they will ask you to do the calculations. So you need to just master to say 180 separation gives you max minimum energy, and therefore most stable. The one that is eclipsed will give you the maximum energy and therefore least stable. That's in terms of stability when you are comparing. So I think that's that on this particular segment of acyclic molecules. So what we'll do is you can try probably to go through yourselves if at all there's any acyclic questions that have come, and then see if at all you'll be able to come up with the structures. If you have difficulties, not to worry yourself, not to worry yourself. We'll go through together. So I think this is where I'll end for today. This is going to be the last part. So you are drawing the conformation, the conformer of butane. This is 2-butane, viewing along C2-C3 bond. This, if you say this is the structure that you have drawn, if this is the first structure you have drawn, this is how you're going to draw it at eclipse. So it's going to come out at total eclipse, and total eclipse is 0. All right, you are observing from here. So if you check, that's on the top, that's on the top. This is left, this is right. You can distinguish because they are the same. But anyhow, this is how it's going to come out. If you view this molecule in that particular state, this is how it comes out. Or if you do now, when you are doing a rotation here, after your first structure, you can do rotation, 60-degree rotation. So what you do is you choose, are you going to be moving the front or are you going to be moving the back? You can only move one. So you have to choose between the front or the back. So if you say, oh no, me, I'll be moving the back, meaning you'll be holding the front constant. The front shouldn't be changing position. It should just be in the same position. If you say, I'll be moving the front, the back should remain in the same position. In this particular example, what was being rotated is the front, the back remained constant. And if you can see CH3, CH3, CH3 pointing up throughout. Okay, so this is pointing up, pointing up, pointing up, pointing up. It wasn't changing. So this is what was being rotated. So once you do a rotation, this is the structure you're going to get. 60-degree difference there, gouge. You do a 180 rotation, this comes there, this comes, so this moves 60 degrees this side.